the last few lectures, we have been talking about LCR circuit, and through several examples, we have tried to explain various concepts connected with that circuit, as well as we talked about a very interesting phenomena of resonance that occurs when the impressed frequency equals what is known as the natural frequency of the system, that is 1 over square root of LC. In the last lecture, we discussed the role that power factor plays in AC circuit. Let me briefly summarize what we did last time. So, first thing is that the power delivered to a load in a DC circuit is simply given by the product of current with the voltage. This is a simple multiplication. Now, in AC circuits, other than resistances, there are elements such as inductors and capacitors, and the problem becomes more complicated because the currents that they deliver are not in phase with the voltage. So therefore, when we add currents or when we find out currents for circuits which contain capacitors, inductors and resistance, there is a little more complicated way of adding them, taking care of their phases. So this is not true of AC circuits in general. The power that is delivered to resistors, this is what we have been calling as the active power. This is either active or occasionally we have also called it true power. The reason why you call them active power is because this power may be used for doing useful work such as heating, lighting, etc. So active power can do useful work. And as I pointed out, this is usually measured in watts or kilowatts. For a capacitive or an inductive load, the current is out of phase with the voltage by pi by 2. In case of a capacitor, it leads, and in case of an inductor, it lags. So capacitors and inductors, phase difference between, let me just call it delta phi. It leads in case of capacitor, lags in case of inductor, and that's equal to pi by 2. So here it leads and here it lags. Well, I meant current leads and current lags. Now, for a general AC circuit, the current may either lead or lag depending upon which reactance is more. So, for LCR circuit, current may lead or lag depending on reactance value. This cosine of this phase, cos phi, this is called the power factor. Now, let us look at what is known as a power triangle. Remember the three basic elements L, C and R which contribute to electrical power in an AC circuit. They are represented by three sides of a right angle in a impedance triangle. So let me first draw an impedance triangle. So an impedance triangle looks like this. This is your resistance R, which is equal to Z cos phi. And this is the reactance X, which is the net reactance that comes out of the capacitive reactance and the inductive reactance, and that's equal to Z sin phi. And the impedance itself is represented by the hypotenuse Z. So this is my impedance triangle. Now suppose I multiply the three sides of this impedance triangle by I square. Let's see what type of things do I get. So firstly, I have, so let me say that multiply by I square. So what I have then is that when I multiply the resistance arm by I square, I get I square R, which we have called as the active power. So active power I will represent by P, and that's equal to I square R, which is measured in watts. The other side, which is the reactive power, is obtained by multiplying the side reactance X by I square. So that is I square times X, and this is measured in volt ampere reactive. The hypotenuse, when multiplied by I square, gives you the apparent power. Let's represent it by S so that it doesn't confuse with R. So that's equal to I square Z, which is measured by volt ampere. So let us draw this triangle here. So what I have here is this. This is the side P, which is my active power. This is the side Q, which is the reactive power, and this is the side S, which is the apparent power. And this angle here is phi, cosine of which is the power factor. So my S is V times I will not repeat it, but it is measured in volt ampere. The side P is V times I times cosine of phi, that is measured in watts, and the reactive power is V times I times sin phi, that is volt ampere reactive. Now suppose I took an inductive case. So for an inductive circuit, my X is XL. In that case, the power triangle will look like this. This is my power P, the active power. Remember, the active power is always along the current direction. And this is my reactive power Q, and this is the apparent power S. And you can see that the current lags the voltage because S is nothing but Vi. So this is current lags the voltage. And in the capacitive case, this triangle will simply become slightly different, and that is the way I would do it, with this becoming equal to P, this becoming equal to Q, and this becoming equal to S, and this angle is phi. And as you can see that the current which is along the direction of P actually leads the voltage. Then what we did is to point out that this power factor plays an important role in transmission lines. And that is because the reactive power, which is actually a wasteful power, that tells us that the amount of power that is actually being produced is not all going to service the load. And one of the functions or one of the responsibilities that we have in constructing transmission lines is to reduce the effect of such lagging, and this is usually done by compensating factors, by substituting capacitive elements in the circuit. So let me illustrate this with another example. So let me say that this is my voltage, AC voltage V, and this is my load, which typically consists of R as well as L. So I am not really writing down what is it. And we have seen that in order to compensate it, I need to put capacitance here. In this specific example, suppose my input voltage is 220 volts RMS. And let us suppose that the current I is 0.5 ampere, of course again RMS, and the current lags the voltage by some angle. So let's say 75 degrees. Now what we need to do is to calculate the active power, reactive power and the apparent power. Okay. So notice that the apparent power is very easy to calculate because this is the product that we have. So that's equal to 220 into 0.5, that is the current, which is equal to 110, this time volt ampere. Now what is my true power? My true power is 110 apparent power multiplied by cosine of phi. So cosine of 75 degrees. If you calculate this, this turns out to some 28.47 watts. Since it's true, it's in watts. The corresponding reactive power obviously is going to be large, because as you notice that the apparent power is 110, whereas the true power is only 28.47, indicating a small power factor. So this would be given by 110 sine 75, and that is works out to 106.25 volt ampere reactive. So this is obviously not a great situation to happen, because a lot of power that is delivered to the circuit are going waste, and that is the reason for which we attempt compensation, which we have discussed in detail. Now what I am going to do today is to take up one of the very special cases of LCR circuit. That's a circuit for which the resistance is taken to be 0, which is known as LC circuit, and we will see if the LC circuit is provided with an initial source of energy by initially charging the capacitance, then that circuit can provide sustained oscillation. But before I do that, let me first recall the dynamics of what is known as a one-dimensional harmonic oscillator, and that picture is something like this. You have essentially a mass which is connected by a spring, the other end of the spring being fixed to a vertical wall, and this mass is initially pulled from its natural unstretched position, and so let me take this unstretched position to be x equal to 0. That is the origin from which I will measure everything. So what I do is that I stretch this mass such that this mass is at a distance, let's say x0 from this initial point, and release it. So at that position what happens is the velocity of the mass is equal to 0. So this is mass m, this is spring constant k, and so this, let me say this is at time t equal to 0. My velocity is 0, but since the spring has been stretched by an amount x0, there is a spring energy there, and so the spring energy, which is the potential energy, so let me represent it by U. So U is equal to U max is equal to half k x0 square, and the corresponding kinetic energy is equal to 0 because the particle has 0 velocity. Now when we leave this mass, when we release this mass, this will start moving to the left, and for suppose the I still have x greater than 0, so from t equal to 0 to t equal to some time period t divided by 4, my x is still greater than 0, velocity is still towards the left. So what happens in that situation is that I have a spring energy U which is equal to half k x square, but this time the kinetic energy is not equal to 0, but it is half mv square, where v is the instantaneous velocity between these two limits. So now what happens is this, that this mass ultimately reaches the equilibrium position. Now what happens at the equilibrium position is the following. So as it is moving towards the left, when it reaches x equal to 0, the time t is equal to t by 4. So let me redraw that picture. So this has just reached the point x equal to 0. Now at that stage there is no spring energy, so u is equal to 0, but the velocity is maximum here, so let me call it v max. So the kinetic energy is half m v max square. Obviously this kinetic energy must be equal to the maximum spring energy which was there at the other end. So kinetic energy is at its maximum, k max. Now this mass obviously starts moving still to the left, compressing the spring, and now x becomes negative, but so from t equal to t by 4 till t equal to t by 2, x is less than 0, the velocity is in principle v, which is less than v max, so kinetic energy is there, which is half mv square, where v is the instantaneous speed, and the potential energy of the spring is half k x square, where x is the compression that is there. Now at t by 2, the compression is maximum, and by conservation of energy we know that the amount of compression must also be equal to x0. So at that stage once again the potential energy of the spring is maximum, which is equal to half k x0 square, and your kinetic energy becomes equal to 0. Now the velocity being 0, and since at this stage the spring is compressed, the there is a force in the opposite direction, that is towards right, and now the attempt will be made by the spring to restore to its normal position. And so therefore from t equal to capital T by 2, till t equal to 3t by 4, once again x remains negative, but velocity is towards right but not equal to 0. And so therefore once again what I have is the kinetic energy is half mv square, the potential energy is half kx square, and this continues till 3t by 4. So at 3t by 4, the velocity is maximum, so kinetic energy is half mv max square, and potential energy, because the spring is neither compressed nor extended, is equal to 0. And finally it starts moving to the right, and once again at t equal to capital T, it completes the cycle with all the energy again becoming potential energy. Now look at what happens, that at an arbitrary point, when the extension or the compression was by x, so there is a spring force which acts on the mass, and so the only force that is there is minus kx, but that must be equal to md square x by dt square, that is the mass times the acceleration. So that's equal to minus kx, now which simply is nothing but the equation to simple harmonic motion, and the solution being x equal to x0 cosine of omega t, where omega is square root of k over m. There is no phase which is taken in the solution, for the simple reason my initial condition was at t equal to 0, x equal to x0. Okay, so since at t equal to 0, x equal to x0. So the spring mass system executes simple harmonic motion. And if you plot the displacement of the particle as a function of time, so what you find is that since at t equal to 0 x was maximum, so let me do this. So this is the way the motion continues. So this amount is x0. Now, so this is the simplest example of a system which executes harmonic oscillations without any damping. There is no damping because we have assumed that the mass is moving on a frictionless surface. Now it turns out that there is an electrical analog to it, which is known as the LC oscillation. Let me try to give you a circuit. So I have a circuit with a DC source, a battery. Let's take a resistance to limit the amount of current that is being passed, and I take a circuit which is like this. I will come back to what these things are. I have a capacitance here, and I also have an inductance in this circuit. So notice what I have done here is the following, that there are these 3 points here. Let me mark it 1, 2 and 3. So also label these appropriately. This is L, this is C, and this is of course a source of battery, which is not particularly important for us right now, but let's put it this way. Now notice what happens when I connect 1 to 2. So let me show it by a dotted line because that's not going to be my main part of the circuit. So if I connect 1 to 2, what happens is that this capacitance comes to the circuit, but the inductance being disconnected, so this plays no role in that circuit. So 1 to 2 connected. This, as we know, will charge the capacitor. So the capacitor will be fully charged. And since I have taken this side of the battery to be the positive side, so what will happen is that this end of the capacitor will become positively charged and the right hand will become negatively charged. So let me count the time from the instant when the charge is maximum. So at t equal to 0, Q is equal to Q max. And this charge will continue to be there in the circuit till the battery remains connected. Now once the charge has become maximum, so at this stage of course the transients have died down. So let me also say that there is no current in the circuit because the capacitor does not allow DC to flow through. Now at that stage what I do is I disconnect 1 and 2. So let me make this point little emphasized. So disconnect 1, 2, but connect 1, 3. The result of which is simply, so let me now show it by a solid line. I have an LC circuit, the battery is out of the circuit and it is fully charged capacitor which is there. Now, so obviously, since this end is charged positive, this end is charged negative, when you connect 1 to 3, a current will flow in this direction to begin with, reducing the charge on positive plate and also reducing the charge on the negative plate till the reverse situation happens, that this side has become positive and that side has become negative, and then the whole cycle will continue and this system will show charge oscillation. So let's look at that. So we'll say that current flows so which means di by dt is greater than 0. But notice when my current is there, the charge is reducing, so therefore my I is minus dq by dt. Now if I now look at the Kirchhoff's law for this circuit, now remember there is no battery in this circuit, but I had charged my capacitor initially. So what will happen is this, my circuit equation will become minus L di by dt plus Q by C, which is the voltage across the battery, is equal to 0. Using the fact I is equal to minus dq by dt, I can rewrite this equation as d square q over dt square plus q over LC, I have divided both sides by L as well, is equal to 0. Now you could compare this equation with the equation that I had given for one-dimensional harmonic oscillator, namely d square x by dt square plus k over m x is equal to 0. Both these obviously represent oscillating circuits. We had analyzed this one, but this would mean that the frequency or the angular frequency of oscillation is given by omega equal to 1 over square root of LC. This is for the electrical circuit. Compare this with the mechanical circuit, for which omega, let me call it omega mech, that's equal to square root of K over M. Looking at these two equations, it tells me that the similarity seems to be that the charge is being similar to displacement x in the mechanical circuit. So let me put in this comparison there. The charge q is analogous to displacement x in the mechanical circuit. Now, so what happens is this, that at t equal to t by 4, the energy has, because the capacitors are totally discharged, so the energy that was stored in the capacitor, that is energy that was stored in the electric field, has now been transferred into the magnetic field associated with the inductance. So the electrical energy has been completely transferred to the magnetic energy associated with the inductor. So let me just show you the slide which gives me the energy as a function of time. So you notice that in the beginning my circuit was charged completely. So all my energy was electrical energy. Now with time, the electrical energy gets converted to the energy of the magnetic field, and at time t equal to t by 4, the capacitors are fully discharged and all the energy is in the magnetic field. So therefore, in this diagram, this picture here, that's my UE, and this other one is my UB, which is the magnetic energy. And at any instant of time, my magnetic energy UB is half Li square and electrical energy UE is Q square by 2C. And the total energy, which is sum of this and this, is represented by this horizontal line, that is constant. So U total net is UB plus UE, and that you can write either as QM square by 2C or as half LIM square. So what happens at time t equal to t by 4? Now notice, at time t by 4, my capacitor plates have been completely discharged. Now in such a situation, you would expect that no current will flow because there is no battery in the circuit, there is nothing to provide a current. Because initially you remember there was a current because my left plate was charged positively, right plate was charged negative. So initially I had that, but now Since both the capacitor plates are discharged, I don't expect it. But there is a problem. The current cannot suddenly switch off to zero, because if it did, according to Faraday's law, there would be a very large EMF brought into the circuit. So as a result, what happens is the current continues in the same direction as before, that is the direction in which it was flowing from 0 to T/4, and it will now charge the right plate positive and left plate will become negative till the at time T/2 the capacitors are charged fully again, though their sense in which the plates are charged have now reversed, and the entire energy now is in the capacitor or in the electric field. And this oscillation continues like this for again at 3T/4 and back at T. I will not go through the solution because the equations are very similar, so the solution must be very similar. What is happening is that in the mass spring system, we had a continuous conversion of kinetic energy into potential energy and vice versa. In this case, the kinetic energy is analogous to the magnetic energy, half mv square and half Li square. So what we find is the kinetic energy for the spring mass system, this corresponds to the magnetic energy for the LC circuit, that is half mv square corresponds to half Li square. Now comparison is now clear. Remember, my quantity which corresponded to the displacement was the charge, so therefore the parallel is between the velocity being similar to the current I, which is, as I said, should be obvious because x corresponds to q. But you notice one thing, the role of mass in the mass spring system is taken over by the inductance. So m is L, and if you look at the potential energy expression, which is half kx square, this corresponds to q square by 2c, and since we know x and q are comparable, then my analogy between the two circuits would be the spring constant k is analogous to the inverse of the capacitance, and the total mechanical energy which is the sum of the potential energy plus the kinetic energy. Now that obviously corresponds to the total magnetic energy plus the electric energy, which is potential energy is U electric, kinetic energy is U magnetic, and that is the total electromagnetic energy. So let me put, these are analogies, and that remains constant in both these circuits. So let me give you an example of LC oscillation. Supposing I have an LC circuit with L is equal to 50 millihenry and C is equal to 20 microfarad, and it's given that current is initially maximum. initially actually simply means at time t equal to 0. My question is, how long does it take to fully charge the capacitor? Now notice that we have already pointed out that there is a phase lag between the magnetic energy and the electric energy, which is time t by 4. So here my omega is given by 1 over square root of LC, and that is 1 over square root of 50 millihenry is 5 into 10 to the power minus 2, and 20 microfarad is 2 into 10 to the power minus 5, and that is equal to 10 to the power 3 radian per second. So that tells me that the time period t, which is 2 pi by omega, that if you substitute, you will get it to be 6.3 milliseconds. Now realize what we have been having here is something like this. I have given you a current which is like this, and so this is the current I, and correspondingly the voltage is like this. And this is t by 4. That is the time lag between the voltage maximum and the current maximum, which is t by 4. So my time lag between these two will be 1/4 of this, which is approximately 1.6 milliseconds later the capacitor will get fully charged. Let's take another example. Suppose I have a radio tuner. Remember I told you that a radio receiver or a tuner, it works on the principle of variable capacitors. When you are rotating the dial of a radio tuner, what you are doing is actually to change the capacitor in the circuit. Now suppose I have a radio tuner which can work in what is popularly known as the MW band, medium wave band, and let us say it can tune in the range 800 kilohertz to 1200 kilohertz. And what I have been given is this, that the inductance in the circuit is given to be 200 micro Henry, which is same as 2 into 10 to the power minus 4 Henry. Now my question is that what is the range in which my capacitance varies? So let's look at that. So remember, these are linear frequencies f. So I first need to convert them to the angular frequency. So corresponding to 800 kilohertz, this corresponds to multiplied by 2 pi. So 2 pi into this kilohertz, already 10 to the power 3 is there. So this is 5.03 into 10 to the power 6 radians per second. And corresponding to 1200 kilohertz, multiplication by 2 pi will tell you this is 7.54 into 10 to the power 6 radians per second. So these are omega values. But I know that omega is 1 over square root of LC, which tells me that the capacitance is given by 1 over L omega square. So all that we now have to do is to put the value of L and substitute the values of two ranges of omega. So if I take the first case, omega equal to 5.03 into 10 to the power 6, I get C is equal to 1 over 2 into 10 to the power minus 4, and this is omega square, so it is 5.03 square. So that's about, let's just approximately say it's about 25 into 10 to the power 12. So therefore this quantity, as you can see, it is 1 over 50 in the denominator and 10 to the power 8 in the denominator. So put them back, this gives you about 2 into 10 to the power minus 10, which is same as about 200 picofarad. 1 pico is 10 to the power minus 12. And if you look at the other extreme, then your omega is 7.54 into 10 to the power 6. The calculation is trivial. The corresponding capacitance becomes approximately 90 picofarad. So therefore, your radio tuner must have the ability of varying the capacitors from the minimum of 90 picofarad to a maximum of 200 picofarad. Let's take another example. In an LC circuit, given C is equal to 64 microfarad, the expression for current is given by 2 sine 500t plus 0.4. This is of course in ampere, and the phase constant 0.4 is in radians. I have a few questions. A, at what time t does the current reach maximum? It's actually trivial. Only thing that you have to realize is, since this is the type of expression that I have given for the current, it tells me the origin of time is different from what we have been assuming in our previous discussion. And so I know that I is equal to Im, that's maximum, when this argument here, when 500t plus 0.4, that is equal to pi by 2. So that sine function reaches its maximum. You compute t from this, and that works out to 2.34 into 10 to the power minus 3 seconds. What is the value of the inductance? In order to do that, you have to recognize that this must have been my omega, 500. So omega is equal to 500, and that is equal to 1 over square root of LC. So compute, that will give you L is equal to 1 over 16 Henry. Rather a big value of inductance, but these are all illustrative problems, so it doesn't really matter. What is the total energy? The total energy, I can simply compute the magnetic energy when it is maximum, because I know at that time the capacitor energy is 0. So it is simply half L Im square. Now that I have computed L, so it is half into 1 by 16 and Im was 2 ampere, that's the maximum. So therefore this into 4 and that's equal to 1 over 8 joules. So let me give an illustration. Consider an LC circuit with L is equal to 2 millihenry, C is equal to 80 microfarad, and supposing at t equal to 0 initial charge in the capacitor plate is 4 microcoulomb and the circuit is set to oscillation. So let's look at various things associated with it. First is the frequency of oscillation, which is 1 over square root of LC, and that is L is 2 millihenry, so 2 into 10 to minus 3, and this is 80 into 10 to minus 6 because it's microfarad. So this is clearly 1 by 4 into 10 to the power 4, and that is 2500 radian per second. Now look at the electrical energy, UE, that's Qm square over 2C. Qm is 4 microcoulomb, so it was 16 into 10 to the power minus 12 divided by 2 into 8 into 10 to minus 5, that's 80 microfarad. So that is 10 to the power minus 7 joules. So we have calculated what is the maximum energy stored in the electric field. Now with time what happens is the electrical energy gets converted into magnetic energy and vice versa, means that the electrical energy from being maximum goes to 0 when the magnetic energy goes from 0 to being maximum. And how much is the magnetic energy maximum? Remember, Im is given by Qm times omega, and we have given Qm to be 4 microcoulomb, so this is 4 into 10 to the power minus 6 times 2500, which is 10 to the power minus 2 amperes. So the maximum magnetic energy, let's write it as mag maximum, which is the energy associated with the magnetic field, is half Li square, and since I am looking for the maximum, it is half Lim square, and substituting this I got half 2 millihenry 2 into minus 3 into 10 to the power minus 4 because it's Im square, and that as expected works out to 10 to the power minus 7 joules. I said as expected because obviously at this time all the energy stored in the capacitor has got converted into the magnetic energy associated with the inductance, and this push and pull mechanism where electrical energy gets converted to the magnetic energy and vice versa continues as long as the oscillation persists. So this is about an oscillating circuit, and the only point to realize is that what we have assumed is slightly unphysical, because we have said there is no resistance in the circuit. But then if there were resistance in the circuit, this will lead to damping of these oscillations, just the way the friction would lead to damping in the mechanical circuit. So what we have done in this lecture is to consider LC circuit we have assumed that the capacitor was initially charged, and the only thing that is there now in the circuit is an inductor and a capacitor, and what we found is that there is an oscillation of both charge and current, and the oscillation frequency, so charge and current oscillation takes place. The oscillation frequency or the angular frequency omega is given by 1 over square root of LC. What we did is to also establish a parallel between this oscillating circuit and a mechanical circuit consisting of a mass and the spring system. Without having any friction. The comparisons were as follows: the charge Q corresponded to the displacement of the mass, the current was parallel to the velocity, inductance L was similar to mass, the capacitance was 1 over K, correspondingly the electrical energy of my LC circuit was like the spring energy of the mechanical system, and the magnetic energy was similar to the kinetic energy of the system. And both these systems are conservative systems in that the total energy remains the same.